According to a lot of the mainstream media, the theory of intelligent design is a faith-based idea. And in saying that, they want to dismiss it as something that has no basis in science. But the media has confused a fundamental issue. They're confusing the evidence for the theory with the implications of the theory. The theory of intelligent design may well have implications that are supportive of theistic belief, but the theory is not based on theistic belief. It's based on the discovery of digital code in cells, miniature machines in cells, the fine-tuning of the laws of physics and chemistry, and standard ways of scientific reasoning about the remote past in the history of life. Impressed to see that there would be question time afterwards and that people would be actually even twittering me. My daughter just taught me to text over Christmas vacation, so they're going to be pretty impressed. Since there will be question time, let me just say a few words about my approach to questions. My first year in graduate school in England, I was attending a lecture on the philosopher Immanuel Kant, and I'd had one course in such philosophy when I was an undergraduate, so I was a little bit out of my depth. And about halfway through the lecturer was talking about an aspect of Kant's philosophy that I hadn't actually encountered before, and I raised my hand and asked if he could direct me to a place in Kant's writings where I could read more about the issue that he was discussing. And it was clear it was a question that revealed some ignorance on my part, and there was a kind of quiet shuffling of feet and an awkwardness. After the lecture was over, my supervisor, who was an English don of the old school, took me aside and he said in his high Oxbridge accent, he said, "Meyer," he said, "I know in the States you've learned that the only stupid question is the one you didn't ask." Then he paused and said, "It's different here." Well, there will be some time for questions afterwards, and it's American rules, okay? So I'm not sure how many we can field, but do feel that any question is fair game. I want to talk tonight about signature in the cell, the case for intelligent design based on DNA. And I want to begin with the central question of design and raise the question about Darwin. A year ago, I had the opportunity to go back to England and to lecture in what we Americans would say Shrewsbury, the British pronounce it Shrewsbury, and it's the birthplace of Darwin, and it was the 200th anniversary of Darwin's birth, the month I was there. And all across the world last year, there were discussions of the legacy of Charles Darwin. What did he teach us? What did he leave us? Obviously, the theory of evolution. He proposed a mechanism for that evolution called natural selection. He pioneered a method of studying events in the remote past. But many historians of ideas and biologists and evolutionary biologists and scholars say that the principal legacy of Darwin has to do with the idea of design. In the first slide I have here, Francisco Ayala says that the functional design of organisms and their features would seem to argue for the existence of a designer. But it was Darwin's greatest accomplishment to show that the directive organization of living beings can be explained by a natural process, a fully undirected natural process called natural selection, without any need to resort to a creator or any other external agent. In an article more recently, Ayala has said that Darwin gave us design without a designer, or at least the appearance of design. And that's the critical Darwinian concept. Next slide, please. When it pops up, it'll be a quotation from Richard Dawkins, who says that biology is the study of complicated things that give the appearance of having been designed for a purpose. We're a little too numerous tonight for me to do my usual kind of teaching style of Q&A, or of asking rhetorical questions, but let me ask one anyway. What is the key word in this phrase? Obviously, very good. Okay, the obvious, from a Darwinian point of view, you have an appearance, but the appearance is entirely illusory. Things look designed, living systems look designed, but they look designed because there is a purely undirected natural process that can produce that appearance without itself being designed or guided in any way. Natural selection can mimic the powers of a designing intelligence, say the Darwinians, but it is not designed or guided in any way. Now, why do the Darwinians say this? This is a classic Darwinian point of view. And it sounds counterintuitive to many people outside biology, but it actually makes sense if you understand this from a Darwinian point of view. I got a little picture here of a sheep, all right? And I want you to do a little thought experiment with me. This goes back to the 19th century. In the 19th century, biologists were very impressed with what they called adaptation. They noticed that organisms seemed well adapted to their environment. Fish live in the water, they had gills and fins. Birds fly in the air, they have wings. Animals that live in cold climates have thick fur or feathers. For example, like this sheep. Now, if you, in the 19th century, it was well known that human breeders could actually cause animals to adapt to their environment. If you wanted to, say you were in the far north of Scotland, and you wanted to breed a woollier breed of sheep, what would you do? Well, in the 19th century, it was well known you could choose the woolliest males and the woolliest females and allow only them to breed, such that over a succession of generations of choosing only those woolliest animals, you would end up producing a much woollier breed of sheep. Now, Darwin's insight was that nature could accomplish what the human intelligent breeder could accomplish. He didn't use this example, but if we adapt it to a Darwinian point of view, we could imagine a series of very cold winters. And if you had a series of very cold winters such that only the woolliest sheep survived in each successive generation, wouldn't the net result be the same as with the artificial selection of the breeders? In other words, nature would be killing off all but the woolliest in each generation, but that would cause only woolly ones to be left to breed, and the woolly characteristic would be amplified over time, thus causing the sheep to be adapted to their environment. In other words, Darwin was able to provide a naturalistic explanation for the phenomenon of adaptation, which to many 19th century biologists bespoke design. If organisms are adapted to their environment, if there's a fit between the environment and the organism, it was thought perhaps that was best explained because the designer had designed the organism to survive and thrive in that environment. But Darwin gave an account of that adaptation without any need for a designer. So he eliminated the need for intelligent design. Now, a couple slides forward, there's another rhetorical question with a sheep on it for our guys in the back. And the question is essentially this. Is adaptation the only appearance of design? And if not, has natural selection explained all the others? It might be that Darwin has provided a perfectly adequate explanation of adaptation, at least the minor variations that occur that cause animals to adjust to changes in their environment, but that he hasn't explained, or his modern followers haven't explained, for example, the very large-scale changes that occur in the history of life. In evolutionary biology today, in biological literature around the world, there are an increasing number of scientists who are questioning the creative power of mutation and selection. There's a group of scientists called the Altenberg 16 who have made a lot of news this last year, all evolutionary biologists who are increasingly skeptical about the creative power of natural selection, and they're calling for a new theory of evolution. Tomorrow, in the event discussing the Cambrian explosion, both the film and several of the scientists talking will be raising questions about the creative power of Darwin's mechanism of natural selection and its ability to produce fundamentally new forms of life from simpler pre-existing forms. Now, that's not what I'm going to be discussing tonight. Next slide. Instead, I'm going to be looking at a more fundamental issue, not the question of how you get new forms of life from simpler pre-existing forms, but instead the question of how you get life in the first place. What we see on the screen behind me is Darwin's famous tree of life picture of the history of life. It's a diagram that depicts the change that he envisioned taking place over time one axis is time, that's the vertical, and then the horizontal axis is change in form. So the tree of life is meant to convey the idea that over time, from the very simplest form of life, there's been a gradual morphing or changing of organisms in their form until at the top of the tree, and the branches at the top are representing all the forms of life that exist today, whether we're talking about reptiles or birds or bacteria or whatever it is. But at the very base of the tree, there's a mystery. And that mystery has to do with the origin of the very first life. Now, Darwin was well aware of this in his time, but he didn't attempt to solve it. He was more focused on biological evolution. After Darwin, there was another theory that came along called chemical evolution that attempted to explain how you got that first simple cell from simpler pre-existing chemicals. And what I want to look at tonight is whether or not those theories have explained away the appearance of design, or any appearance of design that might reside at the point of the origin of the first life, or another way to say that is that might reside within the simplest living cell. Next slide. Now, in the 19th century, as I mentioned, Darwin neither explained nor attempted to explain the origin of the very first life. He had a few speculations about it that he wrote to colleagues in letters, but he didn't attempt to develop any kind of systematic theory. Yet, scientists, even very soon after the publication of The Origin of Species, were quite convinced that Darwin had explained away all appearances of design, at least many of his followers and the evolutionary biologists that followed in his wake. Why was there such confidence that Darwin had explained away all evidences of design when it was also known that he hadn't explained the origin of the first life? Well, the simple answer to that, and the next slide underscores this, is that nope, we've got to go back one, sorry. The quote, yeah, I was on the quote from Huxley. They're very, very, very good. In the 19th century, the cell was thought to be extremely simple. It wasn't thought to be the kind of thing that manifested any intricacy or evidence of design. In fact, one of Darwin's key followers, Thomas Henry Huxley, believed that the fundamental substance that made up life was something called protoplasm. And in Huxley's view, protoplasm was a simple chemical substance that could be produced by a few simple chemical reactions. Another staunch Darwinian on the continent, Ernst Haeckel, had the same view, and they both had quotations like the one, or made statements like the one in the quotation behind me, that the cell is a simple, homogeneous globule of undifferentiated plasm. It's like Jell-O. It's not very complicated. And if you think of life in that way, even if you don't have a detailed theory of the origin of life, you're going to assume that it's going to be a pretty easy task to explain away the origin of life by reference to a few simple chemical reactions. Now, that view changed gradually. By the 1890s, we knew a lot more about proteins, and in the 1920s and 30s, there was a theory of the origin of life that was devised by a man named Alexander Oparin, a Russian scientist. And that theory attempted, in a very Darwinian fashion, to provide a step-by-step account of the growing awareness that scientists had of the complexity of the cell. But in the 1920s and 30s, that awareness was still very dim. All that really changed beginning in the 1950s and 60s with what historians of biology now call the molecular biological revolution. And we can have a look in the next slide at the fearless leaders in that intellectual revolution, Watson and Crick. They made a discovery in 1953 that is, of course, well known to almost all of us. It was the discovery, or rather the elucidation, of the structure of the DNA molecule. They were first able to determine that DNA had this beautiful double helix structure, and that shook the scientific world. There were parallel discoveries going on in the field of protein chemistry, and so side by side, science was making progress on gaining an understanding of what was going on in the inner workings of life, in even the simplest living cell. Now, in the very next slide, we see the chemical structure of DNA that Watson and Crick were able to discover. Now, I think an even more important discovery, or insight rather, came 3 or 4 years later when Francis Crick proposed something called the sequence hypothesis. And the sequence hypothesis, next slide, was the recognition that along the spine of the DNA molecule, there are 4 chemical subunits called bases that function just like alphabetic characters in a written language or digital characters in the machine code, which is to say, it's not the shape or the chemical structure of those subunits that causes them to perform the function they do. Rather, it's the sequential arrangement of those bases, those chemical units or sections of code. You might think of a group of Scrabble letters. I have a few up here on the podium with me. If you've got a pile of Scrabble letters on the side of the board, they're not going to do anything for you. You won't score any points in the game. But if you arrange them properly to spell words, and you put them on the right squares, you're going to get points. In other words, it's the sequential arrangement of the letters that allows them to perform a function in that game. The same thing is true in life. It's the sequential arrangement of the bases that allow them to perform a function. And the function that they perform, which was what Crick anticipated, is that they provide instructions for building the critical proteins and protein machines out of which allow the cell, or which keeps the cell alive. Proteins perform all the... We just got me back. Okay. Proteins perform all the important jobs in the cell. They are enzymes which catalyze reactions. They form structural parts of larger machines. They help process information. You can think of proteins like the toolbox, or the toolbox of the cell. Inside the toolbox are lots of different types of tools. Each one has a different shape, and each one can do a different job in virtue of its shape. A hammer can hammer a nail because of the shape it has. You wouldn't use a saw to do that. Well, proteins have this same kind of feature. They have complex three-dimensional shapes or structures, and in virtue of those structures, they can perform different functions. Now, we can move forward on the slide past the DNA. There's the DNA. Okay. Now, proteins are made of smaller units called amino acids. And so what I want you to keep in mind now is two different kinds of molecules that are inside cells. There's the DNA molecule, and we're going to come back to that in a minute, and there's the protein molecules that the information on DNA encodes for. The instructions on DNA direct the cell and tell it how to build the proteins and protein machines that this cell needs to stay alive. Now, here's a child's toy. They're called Snap blocks. When my kids were little, I stole them from them. I don't know that they've ever really gotten over that. They're teenagers now, so on the box it said ages 2 to 4, so I don't think they're missing them too much. But in any case, I'm using these to illustrate the relationship between amino acids, which are the building blocks of proteins, and proteins, which are long chains of amino acids, which fold into intricate three-dimensional structures. And the idea here is that if we go, let's go past that slide showing the amino acids and their chemical formulae. There'll be a test on that afterwards. These are some pictures of different proteins that you can find on the internet. And the proteins have these beautiful three-dimensional structures. It turns out that these three-dimensional structures are critical to the jobs that proteins perform. Next slide. The proteins, it turns out, have an intricate hand-in-glove fit with other molecules in the cell, either the molecules that they are binding with to form structural parts or the molecules that they may be involved with in chemical reactions. This is a protein that's involved in just breaking apart a two-part sugar. Notice that there's a beautiful hand-in-glove fit between the barbell-shaped disaccharide and the protein into which it nestles. And it's in virtue of that fit that the chemical reaction that the protein catalyzes can take place. It breaks that bond apart in this particular case. And that's the story with proteins over and over again. They have beautiful three-dimensional structure, but that three-dimensional structure derives from the precise arrangement of the amino acids in these long linear chains. If you get the arrangement of amino acids just right, the protein is going to fold up into the structure that's necessary to perform a function. If the arrangements are wrong and you get the amino acids, whoop, dropped one there. If you get the amino acids to, if they're arranged in the wrong way, you may not get a fold and a nice structure, and you may lose the function that the protein performs. So the amino acids have a property that can be called sequence specificity. If something is sequence specific, the function of the whole depends upon the precise arrangement of the parts. Think of some other things that might have sequence specificity besides proteins. A couple things come to mind: human language, computer code, and the arrangement of proteins, or amino acids in proteins. Now the question is, how does the cell know to put the amino acids together in the right way so the proteins fold properly? Well, that's where we come back to DNA. And this is what Francis Crick anticipated in 1957, that the information encoded along the spine of the DNA molecule, the precise arrangement of those bases, those chemical subunits, was conveying instructions that directed the construction of the proteins. And that's exactly what we now know to be the case. And I now have a little piece of animation that I can show that explains exactly how the digital information that's stored along the spine of the DNA directs the construction of proteins. I usually like to narrate this myself, but it was such a large audience tonight. We have a clip of the narration that we're going to show in just a second with my voice providing the narration in a recorded form. So we're just going to dim the house lights and watch this narration, and then I'll come back and make a few more comments. But again, the big picture here, what's happening, what you're going to see, is digital information in DNA being copied, transported, and then that information on what's called a messenger RNA strand is going to direct the construction of proteins at a chemical factory called a ribosome. Let's have a look. Homogeneous globule of plasm that scientists imagined in the 19th century. In fact, what's really stunning to me, I started out in a field of geophysics in which I was doing digital signal processing. And what's going on, this is a sophisticated information processing system. It's not just that there's information encoded on DNA, it's that there's a whole system for processing that information. And I live up in Seattle today, or now, and one of the big companies up in Seattle is obviously Boeing. And if you go to the Boeing plant today, the people at Boeing use a technology very much like what's going on in the cell. It's called CAD/CAM, Computer Assisted Design and Manufacture, where you literally have digital information directing the construction of mechanical parts. That's what we see, what we've just witnessed here in this animation. That's what's going on inside the cells. So we're looking at some very sophisticated information and information processing technology. Now, that has raised a really important puzzle or mystery. I call it the DNA enigma. And I have a series of slides about that. And I'm going to just talk about what the DNA enigma is not and then what it is. The DNA enigma is not the structure of the DNA molecule. Watson and Crick did a beautiful job of elucidating that in 1953. It's not where the information, next slide, resides. We know that information for building proteins is stored along the spine of the DNA molecule. It's not even, next slide, what that information does. We just saw that in the animation. That information is used to direct the construction, rather, of the proteins and protein machines that were depicted in the animation as well. Instead, the DNA enigma is closely associated with another mystery. In fact, the mystery that Darwin didn't solve back in 1859. The mystery of the origin of the first life. The DNA enigma is not, per se, just the origin of life, but it's intimately connected with that. The DNA enigma is the mystery of the origin of the information that's stored on DNA. It's not what does the information do, it's not where is it stored, it's where did it come from? How did digital code come to be inside a molecule? Where did that information come from? And as I said, that information, that idea, or that mystery is intimately connected with the problem of the origin of life. Now, why is that? Next slide. Here's a quotation from a leading German origin of life biologist. His name is Bernd Olaf Küppers, and he says this. He says, the problem of the origin of life is basically equivalent to the problem of the origin of information. Now, that actually makes sense. Next slide. If you think about a computer. In fact, I used to ask my students this question. I'd say, if you want to give your computer a new function, what do you have to give it? And they would immediately know the answer. They're under 30, so they're techie, right? They'd know. It's code. You have to give it code, software, digital information. Well, it turns out the same thing is true in life. If you want to build a new form of life from a simpler pre-existing form, you have to have dedicated proteins to service new cell types, and those proteins are built from instructions that are stored in DNA. But at an even more fundamental level, if you want to get life going in the first place, you have to have proteins, and those proteins, again, require information for their construction, and that information is stored in DNA. So building life, we now know, is an information problem. We need information to build life. Now, just a point of clarification about what I mean by information in a biological context. Next slide. There's at least two different conceptions of information. We need one more. That's showing how you need information to build a critter. There we go. This is a little math. There won't be much more math. But there's at least two different concepts of information, and I want to be clear about the one that I'm applying and using in my argument. There's a mathematical notion of information that was first proffered by a man named Claude Shannon in 1949. Shannon had an intuition that information was related to the reduction of uncertainty, and that the reduction of uncertainty was also related to probability. If I roll a dice and throw it on the table, or a single die, there will be 6 possibilities. That means there's a certain amount of uncertainty. I don't know which side's going to turn up. Once something comes up, I've eliminated 5 possibilities and elected 1. If I flip a coin and it comes up heads, I've also eliminated some uncertainty. I've eliminated the uncertainty I had about whether it would be heads or tails. I've elected one option and eliminated another. In the case of the coin, however, I'm eliminating less uncertainty than I am than when I'm rolling the die. So in Shannon's theory, the die, because it's eliminating more uncertainty, is conveying more information when it comes up on, say, a 3 rather than a 1, 2, 4, 5, or 6. Then is the coin, which only eliminates one possibility. Now notice his concept of information is also closely related to probability, because there's a 1 in 6 chance of getting any particular side on the die, and only a 1 in 2 chance of getting any particular side on the coin. The more uncertainty that's reduced, the more improbable the event, and the more information conveyed. So in Shannon's idea of information, information is inversely related to probability. The more improbable an event is when it occurs, the more information is being conveyed, because the more uncertainty that's being reduced. In any case, that's his mathematical concept. And if we can get that equation back up there, I'm sure there's people that want to take notes for the test afterwards. Okay, now there's another concept of information, though, as well, and I want to go one further slide, okay? And this is, and I've got some terminology at the top. Complexity, you need to know, is a synonym for improbability. If something's improbable, it's complex in this mathematical parlance. Now notice there's a difference between the strings of characters, top and bottom. The string on the top is very improbable, so by Shannon's measure of information, it has a high information carrying capacity. Notice that the string on the bottom is roughly the same length, and therefore by Shannon's measure of information, it also has a lot of information. It's a very improbable arrangement of characters in both cases. But can you see that there's an important qualitative difference between the two strings? The one on the top doesn't perform a function. It has no meaning. The one on the bottom does perform a function. It performs a communication function. And it does so in virtue of the sequence specificity, this precise arrangement of the letters in accord with a code or a set of grammatical conventions. Now, in the information sciences, there's a distinction between these two, and there's terminology to capture that. The string on the top has Shannon information. The string on the bottom has what I call functional or functionally specified information. Or because complexity and improbability are related. Some people also refer to this as the top string would be complexity, bottom string would be specified complexity. When we're talking about information in a biological context, we're not talking about strings of characters like the top string. We're talking about strings like the bottom, ones where the arrangement of the bases are specifically arranged specifically sequenced to convey information that is functional, that produces a functional outcome. Now, and this distinction, next slide, was made from the very beginning of the molecular biological revolution by none other than Francis Crick himself. And we see him here saying, Crick, by the way, was aware of Shannon's work and wanted to make clear that when he was talking about information being encoded in DNA, he was not talking about a merely improbable string of characters. He was talking about an improbable string that was also specified to perform a function. Here he says, by information, I mean the specification of the amino acid sequence in the protein. Or in speaking about DNA, he says, information means here the precise determination of sequence, either of bases in nucleic acid, that's like DNA and RNA, or the amino acid residues in proteins. So he's talking about the second kind of information, not the first. That's what we have to explain. When I talk about the DNA enigma, I'm talking about the origin of the information, the mystery surrounding the origin of the information in the DNA molecule, and by information, I mean functionally specified information, not merely Shannon information. Okay, that clarification out of the way, let's press on. Next slide. I first encountered what I call the DNA enigma at a conference in 1985. There were scientists on a panel discussing the origin of life, and nearly all the panelists agreed that the attempt to explain the origin of life by reference to undirected chemical interactions had come to an impasse. Theories about chemical evolution, how you get to the first living cell from simpler non-living chemicals, were coming to a state of impasse. There wasn't a good solution or a good theory on offer. And one of the scientists on the panel was a man named Charles Thaxton, who had just written a book called The Mystery of Life's Origin. I was a young scientist at the time, and it just so happened that Dr. Thaxton was living in Dallas where I was working. I was working as a geophysicist. My job, according to my bosses, who are all Texans, was to look for all out in the guff. There is apparently right now quite a bit of all out in the guff, but it's never mind. Next slide. Anyway, I became fascinated with this because I was at the time working in an information science. I was doing digital signal processing of seismic data, and when I learned that one of the central problems at the core of this mystery of the origin of life was the problem of the origin of the information that you would need to get life going, I became very fascinated with that. A year later, I found myself off to graduate school, and I went to Cambridge, where I wanted to study more about this problem. And I did so in a program in the history and philosophy of science. I eventually did a doctoral dissertation on the question of origin of life biology. And during the period of time in which I began to research this, I wanted first of all to find out how deep an enigma this really was. How deep a problem was this in origin of life studies? This is a subdiscipline of evolutionary biology, and as I got into the literature, I found that it was a very significant problem indeed. There were three basic approaches that I discovered scientists had proposed or discussed, and next slide. And these were chance, necessity, and the combination of the two. And I had in the back of my mind this critical Darwinian concept of design or apparent design. Darwin, of course, favored apparent design. But when we're talking about digital code, or digital information more precisely, stored in a molecule, we're looking at something that has a very striking appearance of design. In fact, no less an advocate of Darwinian orthodoxy than Richard Dawkins himself has said that the machine code of the genes is uncannily computer-like. He says, apart from differences in jargon, the pages of a molecular biology journal and a computer engineering journal are completely interchangeable. The basic ideas of information storage and transmission are there present in both types of systems that are being analyzed, computers and living cells. Fascinating. We have a clear appearance of design, a striking appearance of design. What intrigued me was that there were so many scientists saying, we haven't explained the origin of life, and we haven't explained the origin of the information that makes life possible. So now we have an appearance of design that has not been explained away by any undirected materialistic process. Or do we? That was the question in my mind. And so I began to investigate the different options that I was finding in the technical literature in origin of life research. And I found that there were different approaches to this question, three broad approaches. There's a slide up ahead with a picture of a book by Jacques Monod. If we could go to that, that would be great. Yeah, that's the slide. The title of the book is Chance and Necessity. Monod was a colleague of Crick's, the brilliant French molecular biologist, and in 1968 he wrote a book that was discussing not only developments in molecular biology, but it was really a treatise on the whole scientific approach. And he was arguing that what scientists should do when they're explaining any phenomena is to explain what they see by reference to chance variations or natural laws, which he referred to by the code word necessity. If I drop a ball to the earth, we would say it falls in accord with the law of gravity, and therefore we'd say it falls by necessity. So a law-like explanation is one involving necessity. So Monod says the job of the scientist is to explain things by random or chance variations, law-like necessity, or the combination of the two. And as I was studying these different theories and conjectures and proposals and hypotheses about the origin of the first life, I found that they typically broke into one of three categories. Either these theories relied heavily on chance, or they relied on necessity, or they relied on the combination of the two. I also discovered that early on, fairly early on, scientists had dismissed the idea of chance as having any real explanatory power with respect to this critical problem of the origin of the information in DNA and RNA, the information necessary to make life possible. There were scientists, for example, 2 slides up ahead here, we have a quotation from a man named George Wald. And there were a number of scientists, particularly in the 1950s, who were still talking about chance as Wald put it, the hero of the plot. He said, time is in fact the hero of the plot. Given so much time, the impossible becomes possible, the possible probable, and the probable virtually certain. And the idea was, if you shake, rattle, and roll long enough in that prebiotic soup of all the simple chemicals, eventually you're going to come up with molecules that are chock full of information that can explain the origin of life. It's a famous biochemistry textbook by a man named Leninger, and he was still advocating this idea as late as 1970. But within the technical discipline of origin of life studies, which was very carefully linked to developments in molecular biology, the pure chance hypothesis went pretty much out of vogue, and pretty much out of vogue for good by the mid to late 60s. And I want to explain why that's the case, because I think it's important to understand that. It has to do with something called the problem of combinatorials. It turns out that at each one of these sites in a growing protein chain, I'm going to have to kind of let it lie here, there are many possible amino acids that could attach. There are 20 amino acids that can be part of proteins, 20 protein-forming amino acids. There's actually a larger class of amino acids, maybe as many as 250 or so. But if we just limit our concern to the 20 that can be part of proteins, you can see that very quickly, as the length of the chain grows, the number of combinations that correspond to any given chain is huge. If I've got a 1 in 20 chance of getting a particular amino acid at one site, then I've got a 20 times 20 possibilities associated with 2 sites, or 20 times 20 times 20 possibilities associated with 3 sites. So for any given protein, there's a huge number of other possible ways of arranging amino acids. Now, if it turns out that proteins are rare, functional proteins are rare within that space of possibilities, it's going to be very, very difficult to find even a single protein by chance in, for example, the time of the known universe. Let me illustrate this a little more and see if you can grasp what drove this development in thinking in origin of life studies. Imagine we've got a bike lock that has 10 digits on each dial and 4 dials. How many possible combinations are there? Well, we're always kind of tempted to say 10 plus 10 plus 10 equals 40, but of course it's 10 times 10 times 10 times 10, or 10,000. Only 4 dials, but lots of different ways of combining those 10 digits on each dial. Now, my graphic designer has made me a hypothetical bike lock with 10 dials. Now how many combinations do we have? We've got 10 times 10 times 10 times 10. We've got 10 to the 10, or 10 trillion possible combinations. Now, if you're a thief and you want to quickly crack the code on this, imagine a bike parked out behind the auditorium, and you want to get the lock cracked before the lecture's over, do you have a reasonable chance of getting that done without knowing the combination? Not if you've got 10 trillion possibilities to search. A random search is not going to get the job done. And that's essentially the problem that scientists began to appreciate in spades by the mid-60s, that with proteins, the number of possible combinations is so vast, and the number of trials you have available so limited, even by, say, a 13 to 14 billion-year-old universe, that you're not going to be able to search the number of possibilities. In a short protein, a hormone or something, where you might have just 10 sites, you have 20 to the 10 possible combinations. That's an enormous number. But what about a modest-length protein? I've chosen one about 150 amino acids long. That's short. That's not a long protein. It's very modest length. But with 20 possibilities at each site, there's 150, 20 to the 150 possibilities, or 1 in 10 to the 195th power. Now, there's only 10 to the 80th elementary particles in the whole universe. There's only been 10 to the 17th seconds since the Big Bang. In my book, I go through the math, and I take into account all the relevant factors, and I show that, in essence, searching for even a single gene or protein product of that gene by chance alone is not plausible. It's like the bike lock thief in the back there, who's now on his 42nd guess out of 10 trillion combinations. He's not going to get it done before the lecture's over. It's always going to be more likely than not that he will not find that combination by chance. So considerations like this led many origin of life biologists to simply reject chance outright. There was a critical paper by a man named P.T. Mora in 1964 about this, and a quotation here that I like to read in lectures because I think it gets the point across quite nicely. "Blind chance is very limited," says A.G. Cairn Smith, a Scottish biochemist. "Low levels of cooperation or organization or information, he can produce exceedingly easily the equivalent of a few letters or small words, but it becomes very quickly incompetent as the amount of organization increases. Very soon indeed, long waiting periods and massive material resources become irrelevant." I used to illustrate this to my students with a bag of Scrabble letters, go walk out into the audience, have them each pick out a letter, and then go write the letter on the board to see how much information chance could generate. And of course, invariably, what they would get would be gibberish. Occasionally, get a couple letters like ugh or buh or maybe bat or something, and then the students would start hooting and hollering as if they were showing me up, showing what chance could really do, but I'd always win the argument by just letting the experiment run longer and longer. And this is Cairn Smith's point. If you need a little information, you might get lucky and get her done, but if you need a lot of information, and even single genes, let alone the amount of information you need to build a whole organism, is a lot of information. If you need a lot, chance is not plausible. Now, of course, this doesn't come as any great surprise to any committed Darwinians in the audience or to evolutionary biologists. The standard Darwinian approach has never been to rely on chance alone, but rather chance in combination with a law-like process known as natural selection. And so after it became apparent to many scientists in the 60s that the complexity of the biomolecules, the DNA, the RNA, and the protein, the specified complexity, the informational complexity of these molecules was so vast, and that chance wasn't a plausible explanation for it, scientists began to think about combining chance with natural selection. And that led to a period of time in which there were scientists proposing ideas about prebiotic natural selection, proposing that Darwin's mechanism of differential reproduction, his survival of the fittest mechanism, could explain the origin of the information that you need to produce the first life. But that had a problem associated with it, and one that was recognized and has been recognized repeatedly in the literature. And the problem is that it begs the question. That's, for philosophers, a big sin, okay? It's a logical error. Here's the basic problem. In all living organisms, natural selection ensues once you have organisms that are capable of reproducing, of copying themselves. Remember my sheep example from the beginning of the lecture. If there's a group of offspring that have a variety of characteristics, and one of those characteristics confers a survival advantage, and such that the others die off, that one is going to live to pass that trait on. But if there's no reproduction, you can't have natural selection, almost by definition. In fact, proposing natural selection at a prebiotic level is really stretching the concept to a breaking point, because natural selection presupposes self-reproduction or self-replication, and here's the real kicker. In all living organisms, self-reproduction or replication is made possible by sequence-specific, that is, information-rich DNA and protein molecules. What were we trying to explain the origin of? We were trying to explain the origin of DNA and protein, rather the information in those molecules. And so we invoked natural selection, but natural selection doesn't even become a factor until you already have DNA and protein, information-rich DNA and protein. It's a little like this. There once upon a time was an absent-minded philosopher of science. He was walking home from university one day, preoccupied with deep thoughts about the origin of life. He'd lost his wallet, his keys, his cell phone, all the usual stuff. But this day it was worse. He fell in a big pit. He wasn't watching where he was going. But no problem, he said to himself. I know how to get out of this pit. I'm just going to go home, get a ladder, come back, jump in the hole, and climb out. What's wrong with my story? It begs the question about how you get out of the pit to get the ladder, right? It's the same. This is essentially what's going on with these theories of prebiotic natural selection. And this was very astutely perceived and articulated by Christian de Duve, the Nobel Prize-winning biochemist and molecular biologist who's done a lot of work on the origin of life, written some important books on the topic. And he put it this way. He said, theories of pre-biological natural selection, quote, need information, which implies they have to presuppose what is to be explained in the first place. Okay? It's a begging the question problem. Now, there have been some attempts to get around this by bootstrapping in various ways. And there have been some computer simulations, and in my book I discuss the problem with those computer simulations, which are essentially they're models of, they're simulating prebiotic natural selection in a computer. And there's some problems with those as well, which I detail in the book. And there's another more current model called the RNA world, which does also involve natural selection at a very early pre-life stage. And I'm sure we will probably want to discuss more about that in the Q&A. I don't want to go into it now. Chapter 14 in my book is devoted to critiquing those models of the origin of life, and we can talk about it more later in our discussion. The third approach that I mentioned for explaining the origin, well, explaining anything according to Jacques Monod, is an approach that relies on pure necessity or natural law, or what in origin of life studies became known as self-organization. And there have been a number of these theories, but perhaps the first and most prominent theory was attempting to explain precisely the sequence specificity of proteins and other critical molecules in the cell. And the idea behind it was that just as in a crystal of salt there is a force of attraction, a chemical force that is responsible for the beautiful ordering of the crystalline structure that you often find with salt. Na has a plus charge, Cl a minus charge, plus and minus attract. You get a beautiful matrix that develops. That's a self-organizing process produced by chemical attraction. And the idea that was first put forward, the first self-organizational theory, was put forward by a man named Dean Kenyon and his co-author Gary Steinman in a book called Biochemical Predestination. We have a professor here tonight from Calvin College, so I probably need to clarify this is biochemical predestination, not the Calvinistic kind, okay? The idea here is that you've got forces of chemical attraction that are responsible for the sequential arrangement of the amino acids that allows the protein to fold into its right structure and perform a function in the cell. There was also the hope that perhaps this idea could be applied to explain not only the sequence specificity in proteins, but also in DNA and RNA as well. Well, it turned out that this model unraveled, and the chief architect of the model himself ended up repudiating his own theory. And there's a kind of many-step story associated with this, which I tell in the book. But I want to zero in on the problem of trying to explain the origin of information in DNA by reference to any kind of self-organizational forces of attraction. Dean Kenyon realized quickly there were some empirical results that showed that his idea wasn't going to work for proteins. There were some slight differences of affinity between some amino acids and others, but they didn't correlate to any of the known sequencing in actual proteins. But at a more fundamental level, he realized that if self-organization is going to work, it's got to explain the origin in DNA and or RNA, because those molecules provide the information for building proteins. That's the more fundamental, need in explanation. So I have behind me a diagram, and I wish I had a point. Actually, it's not there. What I have behind me is me. That's disconcerting. Okay, this is the structural formula for the DNA molecule. And I want you to notice a few things. For non-chemists here, it's going to sound like Chinese at first, but hang with me here. Along this, the two sides of the DNA molecule are made of something called the sugar phosphate backbone. The pentagons are the sugars, the circles are the phosphates, and the backbone of the molecule is not the informational part of it. It's the medium upon which the information is inscribed, if you will. Along the interior of the molecule are two copies running in opposite directions of the informational instructions. They're encoded using those bases that I discussed at the beginning of the evening, the A's, C's, G's, and T's, also known as nucleotide bases. Now, it's the specific arrangement of those nucleotide bases that constitutes the information in the DNA molecule. Okay? Now, the question is, could you explain the specific arrangement of the bases by reference to self-organizational forces of attraction? Could chemistry explain that information? Now, there are little sticks that you can see on my figure, and the sticks represent chemical bonds, connection points, where there is a force of attraction holding something together. Notice that there are sticks between each of the sugars and phosphates. Notice that there is a bond as well between each of the bases and the pentagons in the sugar-phosphate backbone. But notice that there are no bonds between the bases in the information-bearing axis, the vertical axis of the molecule on the screen there. There are no forces of attraction whatsoever. It's not a matter of, are there forces that are differential in strength or otherwise? It's just that there are no bonds between those bases. No bonds that could explain their specific arrangement. Notice also that you have a bond between the base and the pentagons, But here's another little factoid that you need to know. It's the same kind of chemical bond in each case. It's called an N-glycosidic bond for chemists who are keeping score back home. And that bond allows any one of the 4 bases to attach to the backbone with equal facility. It doesn't discriminate. Now, that was all probably difficult, but I'm now going to make it simple. I've got a little visual aid here with a message pandering to the local audience, okay? La Mirada rocks, okay? Sometimes I put a Z in there because my students told me that made it even more cool, okay? Now, this is, you might recognize, a magnetic chalkboard. This is a little metallic chalkboard, and there are magnets in the back of these letters. So there are forces of attraction, forces of necessity, if you will, that explain why the message sticks to the medium. Now, that's exactly the same, that's exactly what's going on in DNA. There are forces of attraction that explain why the message sticks to the medium, but those forces of attraction don't discriminate. I can put the L here, here, or here, anywhere I like, okay? And notice that those forces of attraction do not determine the arrangement. I can destroy this arrangement and make another one very easily, okay? So, so let me put it to you now, maybe as a rhetorical question. Oops, but I destroyed the message. Let's go back to the message, rocks. Oh, I dropped it. Let's talk about the message I had at the beginning. Was that the result? Sometimes these visual aids are more trouble than they're worth. What have I got now? Lada Riminara. No, that's not good. It is sick. That doesn't good. Was the message I had at the beginning the result of the magnetism? Okay, that's the key point. Back to the DNA thing. I mean, I'll get myself out of trouble. Okay, let's go back to that DNA picture. Yeah, thanks. If you look at the DNA molecule, I've never gotten applause for messing up a visual aid before, but if you go back to the point I'm making about the DNA is that the arrangement of the bases, which constitutes the informational endowment of the DNA molecule, is not the result of the chemistry attraction that holds the chemistry of attraction that holds the molecule together. The bonds that are involved in the message sticking to the medium don't discriminate. And there are no bonds between the characters, if you will, the bases that constitute the message. So chemistry is not determining sequencing. In my little illustration, back when there was still a message on the board, what was the source of that information? Okay, at least a quasi-intelligent designer, okay? Right. Now, there was a famous chemist named Michael Polanyi who was a friend of Einstein's, who nearly won the Nobel Prize, who wrote 2 brilliant articles in the 1960s that pointed this out. One was called Life Transcending Physics and Chemistry, and the other was called Life's Irreducible Structure. And he made the point that the information in DNA is no more the result of the chemistry of the bonding of the constituent parts of the molecule than the information in a newspaper headline is the product of ink bonding to paper. Ink does bond to paper, but the information is provided by, as he put it rather coyly, an exogenous source, something outside of physics and chemistry. Now, what could that be? When I left for Cambridge in 1986, I had been exposed to some of the early thinking on what's now called intelligent design. Dr. Thaxton, Charles Thaxton, in an epilogue to his book, The Mystery of Life's Origin, had floated the idea that information was, at least intuitively, a byproduct of mind. It was the kind of thing that you expect to come from minds, or that we know typically comes from minds. And he began to think about the idea of what he called an intelligent cause, perhaps playing a role in the explanation of the origin of life. I was intrigued with this idea, but not altogether convinced. And as I left for grad school, I had a burning question in the back of my mind. Could the design hypothesis, could the idea that DNA is pointing to design, be developed into a rigorous scientific argument? And naturally, and this may seem counterintuitive to many of you, but naturally, I began to study the works of Charles Darwin. Not because he had dismissed design in his work, so much, although he was certainly therefore interested in the question of design or apparent design, but also because he had pioneered a rigorous method of investigating the remote past, a method which is sometimes called inference to the best explanation and other times called the method of multiple competing hypotheses. And this quote, which I won't read, is actually Darwin defending the scientific nature of his theory by telling some interlocutors who are objecting to him that he's using a standard scientific method, one that applies to understanding events in the remote past. Now, the idea of multiple competing hypotheses is that if you're trying to explain an event long ago, next slide, actually, I may not have remembered to tell the man in the back, there we go, did you see the Darwin slide just before that, or did I? Okay, you did, very good. Thanks, Jimmy. Anyway, this is a pictorial representation of this standard method. If you're trying to explain an event in the remote past, you typically what scientists do will posit a number of competing hypotheses. And typically they're hypotheses that posit causes. You're looking for a causal explanation of an event, especially if you're trying to account for its origin. And the best explanation is then the one that we know is able to best explain. So the next slide shows the case where we're able to eliminate all but one of those explanations and settle on the one that is best. Now, obviously, I've just begged a question. What makes an explanation best? What is the key criterion? If we say we infer that explanation which best explains the evidence, we still want to know, well, what does it mean to best explain the evidence? And there's been an extensive discussion about this among philosophers of science, but I was impressed in reading Darwin and also his scientific mentor, Charles Lyell, that they had pretty much worked out the answer to this question in very practical scientific terms without the help of philosophers of science, thank you very much. And they had a criterion that made perfect sense, and it made perfect sense to me, having had a background in the geological sciences. They said that the explanation which is best is the one that posits a cause which is known to produce the effect in question. Here's an illustration. In eastern Washington, we have a layer of volcanic ash that you can go and find today. If you're a geologist and you don't know how it got there because you didn't have the opportunity to view it happening, and you want to explain the origin of that ash, you might posit a number of possible causal hypotheses. You might posit a flood, you might posit an earthquake, you might even posit a volcano. Which of those is best? Well, according to Darwin's criterion, the best explanation would be the volcanic eruption hypothesis, because in our uniform and repeated experience, we know that volcanoes produce effects like that, but we have never seen floods or earthquakes doing the same thing. Clear, simple, common sense criterion at the basis of this excellent scientific method. Now, next slide. I was one day reading more about this in the works of Charles Lyell, from whom Darwin got this method of reasoning. And one day I was reading this long, soporific title in 19th century English, and it about had me asleep, The Principles of Geology, being an attempt to explain the former changes of the Earth's surface by reference to, and then suddenly I had a bolt from the blue. The nickel dropped. I loved the phrase. By reference to causes now in operation. The light went on for me. Because I suddenly asked myself a question about this DNA enigma. What is the cause? Here, what is Lyell saying first? He's saying that if we're going to explain an event in the remote past, we should look to our uniform and repeated experience of cause and effect. We should be looking for causes that we know that are now in operation that produce the effect we're trying to explain. We see volcanoes producing ash, therefore we can infer that there must have been a volcano at work as the best explanation for a layer of ash when we encounter it, especially if there's no other cause that we know can do it. So we're looking to causes now in operation. I asked myself a question. What is the cause now in operation that produces digital information? And I realized what you realized a minute ago. There's only one. And that is intelligence. In fact, there was an information scientist who I was reading about the same time who was a pioneer in the application of information theory to molecular biology. His name was Henry Quasler. And he made an offhand comment that had Lyellian and Darwinian implications, I thought. This is what he said. The creation of new information is habitually associated with conscious activity. Habitually associated is like saying uniform and repeated experience. That's what we repeatedly observe. In other words, that's the cause now in operation for producing the critical feature that you need to explain the origin of life. And I began to realize that it was possible to formulate a case for intelligent design based on the same method of scientific reasoning that Darwin had pioneered in The Origin of Species. There's a famous guy up in our neck of the woods named Bill Gates. He's got some little enterprise with software or something. And he made a comment about DNA that I think is very important and suggestive. He said the DNA is like a computer program, but far more advanced than any we've ever created. It's like a computer program in many respects. It also has the same attribute that the identical attribute that a program has, which is that it encodes specified information, functionally specified information. Now that's a very suggestive remark because we know from experience that computer programs, always come from programmers. We know that more generally, information in whatever form we find it always comes from an intelligent source. Whether we're talking about a headline in a newspaper, a paragraph in a book, a hieroglyphic inscription, information embedded in a radio signal, whenever we find information and we trace it back to its ultimate source, we always come to a mind, not a material process. That's what we know from our uniform and repeated experience. So when we find information embedded in DNA, the most logical thing to conclude is that it too had an intelligent source. Now, if I've been up here flipping slides, realizing that we've got this technical problem again. Where are we in the slides? Next one. There's my hieroglyphic inscription, and there's a picture of the book. Okay. In the book, Signature in the Cell, I develop the case for intelligent design in more detail. And I develop it, though, along much the lines that I've been describing tonight. I develop it as an inference to the best explanation for the origin of the information you need to build the first living cell. And in the process of doing that, next slide, I look at the various competing classes and types of explanations that have been offered. Is there another slide after that showing the... Yeah, there we go. I look at explanations that rely on chance. I look at explanations that rely on necessity. I look at explanations that rely on the combination of the two. And I show that, next slide, that in each case, those naturalistic explanations, chance, necessity, and the combination of the two, and many different models manifesting those basic explanatory strategies, have failed to explain the origin of this critical feature of life, the information necessary to get it going. And so I conclude that intelligent design is the only known cause that's capable of producing the information necessary to produce the first life. And therefore, I conclude that intelligent design constitutes the best explanation. Now, I think it's important to point out that this explanation is not an argument from ignorance. 2 slides forward, if I could. I have and then one more. I have a friendly and frequent debating partner named Michael Shermer. He and I debate quite often, and every time we debate, he makes the same argument, and every time I make the same response. And last time I actually said, Michael, I'm going to make the same response, so maybe you ought to just try a different argument this time. But this is what he says. He says that intelligent design is not, this is a philosophical objection, essentially. He says it's a bad argument because it's arguing from ignorance. It's essentially saying natural processes have not been demonstrated to have the power to produce information starting from a chemical state, and therefore intelligent design must have done it. It's like saying candidate A is a good candidate for president because we know that candidate B is such a bad candidate. You're not giving a positive reason for believing that candidate A is a good candidate. That's an argument from ignorance. You're arguing from what we don't know about either candidate B or, in this case, natural processes that can produce information. But this isn't how the case for intelligent design is being constructed. That's not the argument we're making. We are critiquing, I am critiquing the ability of naturalistic processes to produce information. Those critiques are also in the relevant literature in chemical evolutionary studies. But I'm saying that there is, in addition to that, another type of cause, a type of cause of which we know that is capable of producing information. So next slide shows the actual logic of the case. It's not that we're arguing just against natural processes. We're also saying there is another cause which is known to have the causal powers, next slide please, to produce information, and that cause is intelligence or mind or conscious and rational activity. In fact, that's the only cause in the universe of which we know that has the capacity to produce the key effect in question. And therefore, on that basis, we can infer it as the best explanation. So the argument for intelligent design that I'm making is not an argument from ignorance. It's an argument from our knowledge of the cause and effect structure of the world, of what certain kinds of causes can and can't do, or do and don't do, and what other kinds of causes are known to accomplish, in particular, intelligent causes. Now, if we can go about 4 back, there was a little list. I just want to end with a little anecdote. I mentioned Microsoft a couple times. We have at our lab that we helped to start at the Discovery Institute, an independent lab now called the Biologic Institute. And the director of the lab is here tonight, Doug Axe. And at Biologic, a computer programmer started to work. He resigned from Microsoft for a couple of years to help write some code simulating that gene expression system or protein synthesis system that we were showing before, how the digital information in DNA is processed to produce proteins. One day he came into my office and he threw a book down on my table, and it was called Design Patterns. And he said, rather cryptically, "I get an eerie feeling that someone has figured this out before us." And I said, "What do you mean?" And he said, well, first he explained the book. Design Patterns is apparently a standard operating manual for software engineers. And a design pattern is a term of art for a design strategy or a design logic, a way of solving a functional problem, especially in information processing. And my colleague said to me, he said, when I say I get an eerie feeling that someone figured this out before us, what I mean is the same kind of design patterns that we use in modern high-tech digital computers are being used in the processing of information inside living organisms. He says, I'm just learning about this so I can write the code. I'm learning from your molecular guys what's going on. But it stuns me. It fascinates me. Inside the cell, like inside a computer, there's a hierarchical filing system, a system of files within folders, folders within superfolders, superfolders within super-duper folders. Hierarchical organization of information. There's also something that functions like a spell check. If information is being copied and it's not being copied accurately, there's a protein complex, a machinery that locks on, backs up the system, and makes sure that the copying is done over with the correct fidelity to the original message. There's even a way of encoding. It's called nested coding of information, where information is encoded within other information, a technique that's used in cryptography. So when my colleague reacted this way, this was an intuition on his part. I get the eerie feeling someone figured this out before us. But again, I don't think that that's just an intuition. I think there's a logical grounding for a design inference, because each of these design patterns are features that we know are produced by one and only one type of cause, and that cause is intelligence. So for many reasons, I think that the best explanation for the origin of the information necessary to build the first life, and indeed the whole information processing system, can be best explained by intelligent design. And I'll stop there. Thank you. And good
Thank you, Steve. Thank you, audience. This isn't the most plush seating around, so you were very good and patient, and you deserve a break. But before the break, make sure you fill out the card or steal a pen during the break to fill that out. You're going to need it when you come back. Use the order form to go order some DVDs, visit the book tables, buy armloads, use the restroom. We'll be back in 15 minutes to begin the interaction.